Hello, everyone. Welcome back to the Banach Spaces webinar. Today, I'm very pleased to introduce Yuval Wigderson from Stanford. Last week must have been really exciting for the Wigderson family. You know that Avi Wigderson, I think he's joining us today, won Abel Prize in Mathematics along with Loesch. What an amazing and inspiring career he has. And I just want to congratulate on the behalf of this community here, Avi and Yuval and the whole family for this amazing achievement. And I'm pleased to see that today's talk is actually a joint work with Avi. And so Yuval will be speaking on new perspectives on uncertainty principle. Yuval?
Great. Yeah, thank you for the introduction, and thank you for the invitation to speak here. Yeah, as I said, I feel like I am a bit of an interloper in the Banach space community because this isn't really what I think about most of the time, but I'm very happy to come here and to tell you all about these things that I find really interesting. And in particular, you should feel free at any time to stop me and ask any questions about anything because, yeah, as I said, I feel like you may have a lot more to contribute on this topic than I do. So I really want this to be, if you have anything to say, please don't hesitate. Okay, so yeah, so let's get started. So I'm going to be talking about the uncertainty principle. So just to get started, what are we talking about? What is the uncertainty principle? So it all goes back to this famous paper of Heisenberg from the 20s, right at the beginning of the development of quantum mechanics. And what he was arguing in this paper was that it's impossible to simultaneously determine a particle's position and momentum to sort of infinite precision. And the thing that's really sort of revolutionary about this paper is that he was making this claim not as a fact about like our measuring implements or our ability to do scientific measurements, but really about as a law of nature, that there is some fundamental obstruction to knowing both of these things, to arbitrary precision. And Heisenberg's paper was at first sort of just full of physical heuristics and intuitions, but basically immediately afterwards, both Kennard and Weil independently found a mathematical formalism for this notion. So this is how the physicists write it. They write sigma x is the uncertainty in measuring the position, sigma p is the uncertainty in measuring the momentum, and it's lower bounded by a positive quantity. The product is lower bounded by a positive quantity. Here h is Planck's constant. And the point is just that because their product is lower bounded by something positive, one of them has got to be large. So it's impossible for both of them to be arbitrarily small. And one of the things that's amazing about what Kennard and Weil did, and it was realized basically immediately by them and by Bohr and by others, is that this isn't really only a fact about position and momentum. It applies to any pair of quantities, which the physicists call canonically conjugate. So these are quantities that in the framework of quantum mechanics are related by a Fourier transform. So there's this weird fact in quantum mechanics that the wave function of the position is the Fourier transform of the wave function of the momentum. But there are many other pairs of variables in quantum mechanics that are related by a Fourier transform. So other examples include, I guess, like angular position and angular momentum, or the spin of a particle in two separate reference frames, or energy and time. And basically, as soon as it was realized that this was really a fact about the Fourier transform, it became a fact about math instead of just physics, and the mathematicians started talking about this. And so uncertainty principles ever since the 20s have, really gone into a lot of places in math. So I've just listed here a bunch of topics where there are connections to uncertainty principles. So functional analysis, PDEs, microlocal analysis, wavelets. I've also written here signal processing, which is unlike all of these sort of analysis topics. This is really more of a discrete topic. And this was due to work of Donahoe and Stark in the late 80s. They realized that sort of parallel to the big theory, well-developed theory of continuous uncertainty principles, there were also discrete uncertainty principles, and they were motivated from signals processing. And it turns out that these sort of discrete uncertainty principles have really taken off also in these fields like signal processing, information theory. And in general, there's now a whole host of uncertainty principles, and all of them are of the form that it's not possible for a function and its Fourier transform to be highly localized. So we'll see examples of this, but the reason that there are so many uncertainty principles is that there are many different ways of measuring what it means for a function to be very localized, and then an uncertainty principle is a statement that for whatever measure of localization you like, it's not possible for both a function and its Fourier transform to have a small measure of uncertainty, of localization in this notion. So before we get to the details, I just put a slide here about the Fourier transform. I'm sure everyone here knows what the Fourier transform is. I just put it here so we can agree on normalizations. So this is the normalization I'll be using, that the Fourier transform of a function is defined. I put the 2 pi in the exponent, so there's no normalizing factor out front. And basically the only fact that we'll need about the Fourier transform is the Fourier inversion formula, which says that if you know the Fourier transform, you can recover the original function using essentially the same formula. So the only difference is there's no minus sign in the exponent. So you're just integrating f against this complex phase and no normalization or anything. And occasionally I'll need the discrete Fourier transform. So I'm going to be using this normalization. Again, the precise normalization doesn't really matter. I just want to agree on it for once and for all. So in the discrete case, you're dealing with a function on this finite cyclic group. And you define the Fourier transform in basically the same way, except now it's a sum. And I've decided to normalize by 1 over square root n on the outside, just so that in the same way as in the continuous case, the forward and the reverse directions look really the same, except for a minus sign. Okay, so this is the Fourier transform. The final thing I want to mention on this slide is I'm not an analyst, and so I don't want to deal with the technicalities of exactly which functions we'll be dealing with. So for the rest of the talk, I'll never say it, but I will always assume that whatever functions on the real line I'm dealing with are nice enough. If you want to know, for everything that I'll be doing, it suffices for both f and its Fourier transform to be an L1. But if you prefer, you can think of, I don't know, Schwartz functions or any nice class of functions that you like. Okay, so yeah, as I mentioned, there are many uncertainty principles, and I just want to give you an example of, or many examples of them. I don't expect you to remember everything I say on the slide because there's just going to be a bunch of examples, and I'm only putting the slide here so that you can see just the vast array of different types of statements fall under this umbrella of the uncertainty principle. And I've split this into 2 columns. So on the left, I have uncertainty principles for functions defined on the real line, and on the right, I have for discrete functions. So the most basic statement, perhaps, is this well-known fact that if a function has compact support, then its Fourier transform does not have compact support, right? And this fits into this general framework I mentioned earlier, where somehow having compact support is a nice measure of localization. You're sort of bounded in some interval. And if f is nicely localized in this way, then f hat actually cannot be localized in this way. There was a nice extension of this due to Benedict's, who actually proved that if f has support of finite measure, then f hat does not have support of finite measure. And this is stronger because there can be unbounded sets in the real line that still have finite measure. Okay, so this is one class of uncertainty principles that deals with support as a measure of localization. Another class of uncertainty principles was initiated by Hardy, and this concerns localization as measured by decay at infinity. So roughly speaking, I've put this a little vaguely here, but what Hardy proved is that it's not possible for both f and its Fourier transform to decay faster than e to the minus x squared at infinity. And so basically, if you measure localization by how fast you decay at infinity, it's not possible for both f and f hat to decay arbitrarily quickly. Yet another one is the one that we started with. So this is Heisenberg's uncertainty principle, but now I've written it sort of in math language instead of in physics language. So here we're concerned with a function, and we're concerned with this variance functional. So the integral of x squared against the norm squared of the function. And for this functional, you have that the variance of f times the variance of f hat is lower bounded by something, where something is some absolute constant times the product of the L2 norms squared of f and f hat. And of course, I mean, by Plancherel, I could have just written here the 2 norm of f to the 4th power, but I like thinking of it as something related to f times something related to f hat. The connection of this to quantum mechanics, as I mentioned earlier, is that in quantum mechanics, you'd be thinking of f as the wave function of the position of the particle. And then this L2 norm would be 1. And that means that this quantity norm of f squared would be defining a probability measure on the real line, which is sort of the probability of distribution of finding this particle somewhere. And then this quantity really is just the variance of that probability distribution. This is really measuring, something about the variance of the position times the variance of the momentum. And the final example that I'll mention on the continuous side is this theorem that was conjectured by Hirschman and then proved by Beckner, which concerns the Shannon entropy, which is defined here. I won't get into it, but basically it's another measure of localization. If a function has a sharp peak, then it will have very small Shannon entropy, whereas if it's rather spread out, it will have rather large Shannon entropy. And this theorem is again saying that the sum, in this case, the sum of these two quantities for f and for f hat is lower bounded by something. So one of them, they can't both be arbitrarily small. So that's in the continuous case. In the discrete case, it all starts with this theorem of Donohoe and Stark. So here we're dealing with a function defined on this, say, finite cyclic group. And the result is that if I just look at the support of f as just a finite set, so the size of that set times the size of the support of the Fourier transform is lower bounded by n, the size of the group. So in particular, at least one of them has to be at least square root n. Right, and again, this is some sort of uncertainty principle where here the measure of localization is again how small the support is. So it's not possible for both f and f hat to be concentrated on a very small number of values in this group. Donohoe and Stark actually proved a strengthening of this as well. So I've written it here in detail, but you don't have to care about the details. This is just an extension to approximate support. So what this is saying is that I have a function, and what this is saying is that if I restrict f to some set s, then doing so captures a 1 minus epsilon fraction of the L2 mass of f. And similarly for f hat with some set t and some other parameter delta. So this is a weaker, or well, it's a more robust notion than support. It's saying that it's not just the set of values where f is non-zero, but it's a set of values where basically a 1 minus epsilon fraction of like the action of f is happening on the set S. And then the result in this case is that the product of the sizes of these two sets is again at least n times some factor that just depends on the quality of the approximation, these epsilon and delta. There was an extension of this, of the Donohoe and Stark theorem, due independently to Biro, Meshulam, and Tau. I think only Tau ever actually wrote this up, but if n is prime, then you can get, rather than the product of the supports being at least n, you get that the sum of the supports is at least n plus 1, which is substantially stronger because it's saying now, this said that just one of them is at least square root n, and this is saying that one of them is actually at least n over 2. But this is also somehow a more delicate theorem. It doesn't have one of these robust approximate support versions. It's really just about the support. And the final result that I'll mention here is Dembo, Cover, and Thomas proved a discrete version of this entropic uncertainty principle of Beckner. So whatever, now it concerns the Shannon entropy on these finite groups. Again, I won't get into exactly what this means. But again, a function with low entropy is highly localized. And this is saying that it's not possible for f and f hat to both be sharply localized. So yeah, before I move on, are there any questions about any of these examples or anything else I've said? Okay, great. So, actually, before I wrap up, I just wanted to mention that in addition to these many examples with many different types of uncertainty principle, something else that I wanted to point out on the slide is that there are many different proofs. So the results on this slide use a bunch of different proof techniques. And many of them exploit various special properties of the Fourier transform. So for instance, this theorem of Benedict's about the finite measure, that uses the Poisson summation formula. And the standard proof of Heisenberg's uncertainty principle uses the fact that the Fourier transform turns differentiation into multiplication by a variable. And this result of Beckner is actually basically equivalent to Beckner's sharp Hausdorff-Young inequality, which is some deep fact about the Fourier transform on the real line. So yeah, there are many different results here and many different proof techniques, and the proofs generally use many different properties of the Fourier transform. So what will I be telling you about today? So we've just wrapped up the introduction. And the next thing I'm going to be telling you about is this new perspective that we have on the uncertainty principle. And basically what our new perspective is that many of these results can actually be proved using the same very basic framework that doesn't really use any fancy properties of Fourier transform whatsoever. It just uses basically some L1 to L infinity boundedness. And yeah, the miracle is that this one simple framework actually proves very many different uncertainty principles. And then after I explain that, most of the rest of the talk will just be examples. I'll have an interlude in the middle where I'll talk about sort of how general this is and how you can extend this. And then I'll wrap up with a bit more discussion and some open problems. So let me tell you about what this new perspective is. So the first basic observation, which is well known, is that the L infinity norm of the Fourier transform is upper bounded by the L1 norm of f. And this is just a simple computation. So if you think about the absolute value of f hat, by definition, it's the absolute value of this integral. And this integral is just the integral of f against some complex phase. So if I bring the absolute values inside, this is just 1. And so I precisely get the L1 norm of f. Right, so at any point, the value of the Fourier transform is upper bounded by the L1 norm of f. And so taking a maximum, I conclude that the infinity norm of the Fourier transform is at most the L1 norm of f. And in exactly the same way, you can prove the corresponding inequality that the L infinity norm of f is at most the L1 norm of f hat. Right, it's the same proof just because the Fourier inversion formula looks identical to this, except for this no minus sign up here, but then the rest of the proof is identical. So I've gotten these two simple inequalities, and if we multiply these together, we get this inequality in purple, that the L1 norm of f divided by the L infinity norm of f times the same thing for the Fourier transform is lower bounded by 1. And I want to say a couple of things about this inequality in purple. So the first thing that I want to say about it is that it's an uncertainty principle. And so again, an uncertainty principle is just sort of any statement of the form, some measure of localization on f times, say, some measure of localization on f hat is lower bounded by something. And indeed, that's what's going on here, right? This quantity, the 1 norm divided by the infinity norm, is a measure of localization. If your function is sort of a very narrow peak, then this quantity will be very small, whereas if it's highly spread out, this quantity will be very large. So this really is an uncertainty principle for this measure of localization. And of course, it was very simple to prove. It just required these simple facts about this L1 to L infinity boundedness. But the other thing I want to say is, I'm going to be a little grandiose here, but I'm going to say that this inequality in purple is really the uncertainty principle. So this very simple inequality that we derived using this two-line argument is what we call the primary uncertainty principle. And it's from this one inequality in purple that we'll derive all the other uncertainty principles that I'll tell you about in this talk. So although it was sort of basically very easy to prove, it's actually sort of capturing a lot of the entire content of uncertainty. So are there any questions about this slide before I move on? Okay, so the next thing I want to tell you about is how you use this primary uncertainty principle to derive other uncertainty principles. So, right, we have this basic inequality, and suppose we're trying to prove some other uncertainty principle. So we have our favorite functional L, which is supposed to measure localization somehow. And we want to prove an uncertainty principle of this form, that L of f times L of f hat is lower bounded by some constant, say. How do we do this? The idea is that this primary uncertainty principle contains all the uncertainty. So this inequality in purple captures everything we need to know about the relationship between f and its Fourier transform. That's all the uncertainty. And everything else we're going to do is going to work on the level of a single function rather than a pair of a function and its Fourier transform. So it suffices to prove an inequality of this form. If we can prove that for any function g, this L of g is lower bounded by some constant times the L1 norm of g divided by the L infinity norm of g. If we can prove such a bound for any function, then we can plug in g equals f and g equals f hat into this primary uncertainty principle, and we'll get that L of f times L of f hat is lower bounded by some constant times this thing, and this is lower bounded by 1. So, right, this inequality star is giving us all the uncertainty, and then it just suffices to prove an inequality concerning just a single function, g. And in fact, this method is more robust, right? I could also, rather than this, I could prove that L of g is lower bounded by, let's say, some power of g1 divided by g infinity, or really anything else. If I have any sort of way of lower bounding L of g by some function of the L1 divided by L infinity norms, I'll be able to use this technique. And I see that there's a question in the chat. How do I formally define uncertainty principle? Yeah, so I don't think there is a formal definition. If you read like surveys about the uncertainty principle, they'll tell you that the uncertainty principle is sort of a vague term, which just captures this notion that it's not possible for f and f hat to both be sharply localized. So yeah, I don't have a good definition. And I think there are some things that you could debate whether or not they're called uncertainty principles. But to me, it really is, you want to deal with some functional L like this, which you should believe is somehow capturing localization, which is supposed to mean that if your function is a very narrow peak, then it's supposed to be large, and it's supposed to be small. And on the other hand, if your function is sort of nicely spread out, then it's supposed to be large. And then an uncertainty principle is just any statement of the form, that thing for f times that thing for f hat is large. But yeah, I don't think there is a formal definition as far as I know. Yeah, any other questions about this overview of how this works? Okay, so from now on, I'm mostly going to be doing examples. So let me start with the examples. So the first example has to do with support size. So what are we going to do? For any function g, its L1 norm is just defined like this. It's the integral of the absolute value of g. And in this integral, I can replace the domain of integration by just the support of g, because it's 0 outside of its support. And now I can use, I guess, Holder's inequality, or this is more simple than Holder's inequality, really. But this is upper bounded by the Lebesgue measure of the support times the L infinity norm of the function. Right? And if I rearrange this, I get one of these inequalities. I get that the support, the measure of the support of g is lower bounded by the L1 divided by the L infinity norm of g. And I'm sorry, I realized that I wanted to mention on the previous slides, let me go back for a second, that every time I'll prove one of these inequalities, it will always be in blue. So be on the lookout for these blue inequalities. They'll always be of this form. So what we got here from the simple computation is one of these blue inequalities, that the support size of g is lower bounded by the L1 divided by L infinity norms. And once we get this, we can plug this into our framework. So if we're looking at the support of f times the support of f hat, I plug in this inequality, I get the L1 norm divided by the L infinity norm for f and for f hat. And then by the primary uncertainty principle, this is at least 1. And so this is how we can prove an uncertainty principle for the support size, that it's not possible for both f and f hat to have supports of measure, let's say, both less than 1. However, this is actually a pretty underwhelming example. And the reason it's underwhelming is that I mentioned to you this result of Benedict's, which actually says that the correct answer here on the right-hand side is infinity rather than 1. And I don't know how to prove that using this technique. So I just started with this example because it's very simple, but it's a little underwhelming. The other reason that I started with it is that actually in the discrete setting, it actually does something more contentful. So in the discrete setting, if you'll remember, the Fourier transform, I define it with the square root n on the outside. And so in this case, what you get is that the L infinity norm of the Fourier transform of f is upper bounded by the L1 norm of f divided by square root n. And so what that means is that in the discrete setting, this primary uncertainty principle that we get is actually of the form the L1 divided by L infinity norms for f times that for f hat is actually lower bounded by n, the size of the group, as opposed to just 1, which is what we were getting in the continuous setting. And because this is what the primary uncertainty principle looks like in the discrete setting, if you apply the same argument on the left, in the discrete setting, you actually recover this Donahoe-Stark uncertainty principle, that the support of f times the support of f hat is actually lower bounded by n. So although in the continuous setting, this was pretty underwhelming, in the discrete setting, this was actually really giving you a contentful result, which is this Donahoe-Stark uncertainty principle. Okay, so that's the first example about supports. Let me move on to my second example, which is about approximate support. So here's the definition that I'll be using now. We're going to say that a function g is epsilon supported on a set E if the set E contains a 1 minus epsilon fraction of the L1 mass of g. And again, this is some good approximate notion of support. It's saying that outside the set E, only an epsilon fraction of like the action of f is taking place. And a basic result about a basic uncertainty principle for this notion of localization was given by Williams in the late 70s. And what Williams proved is that if f is epsilon supported on some set S, and f hat is, let's say, delta supported on some set T, then the product of the Lebesgue measure of S times the Lebesgue measure of T is at least 1 minus epsilon times 1 minus delta. And you'll notice that if you plug in epsilon and delta equal to 0, you get the result on the previous slide, which is just that the product of the supports, the measures of the supports is at least 1, which was not very interesting. But actually, Williams' result actually is interesting, or more interesting. And the reason is that one of the intuitions that people have about the uncertainty principle is that if f has some fundamental length, so if there's some interval of some length that's sort of capturing all the action of f, then the fundamental length of f hat can't be much smaller than 1 over the fundamental length of f. And that's really what this is saying, in some sense, that if f is basically mostly concentrated on this, say, interval s, and f hat is mostly concentrated on this interval t, then the product of the lengths of these intervals can't be much smaller than 1. So this is actually capturing this actually meaningful notion of the uncertainty principle. And how do we prove this using our technique? Well, this is the definition of epsilon support. It's that this is just the definition, what I wrote on the first slide. And again, on the right-hand side, I can use the simple inequality that this is at most the measure of E times the infinity norm of G. And if I rearrange, I get that the measure of E is at least 1 minus epsilon times this ratio of norms. So I get one of my blue inequalities, and if I apply this for G equals F and G equals F hat, I find that the size of S, the measure of S times the measure of T is at least, 1 minus epsilon, 1 minus delta times these ratios of norms, and then by the primary uncertainty principle, we get the lower bound that we claimed. I should mention that this is actually basically Williams's original proof. This technique that we're postulating in this paper is not really new. So Williams was using this technique already in the 70s. The thing that we think is new in our paper is that before this, no one was really doing this separation of you first prove this basic primary uncertainty principle, and then you only prove bounds for a single function. And we think that this separation is really powerful, and it allows you to sort of prove more uncertainty principles and to realize more of these connections. Many of the things we're doing aren't really new. So for instance, this theorem of Williams with its proof was already present in the 70s. Okay, so any questions about this example? Okay, so before I move on to more examples, I promised you this interlude on how general this is. So again, what are we doing? What we're doing is we prove this primary uncertainty principle, this fact about the product of the ratios of norms. And once we have this, we only use what I call here universal bounds. So we just do things that deal with a single function as opposed to a pair of functions. And in order to prove this primary uncertainty principle, all we needed were these very simple L1 to L infinity boundedness of the Fourier transform and the inverse Fourier transform. And so what that means, if you abstract that away, is that if I give you any linear operator with these properties, that its L1 to L infinity norm is bounded by 1, and its inverse also has bounded L1 to L infinity norm, then I can derive the same sort of primary uncertainty principle, now dealing with F and with AF. And it's the same proof. It's just you multiply together what this inequality means with what this inequality means, and you precisely recover this primary uncertainty principle. And the point is, once you prove one of these primary uncertainty principles, now you can derive any other uncertainty principle you like, just by, again, only dealing with things that deal with a single function. So in this framework, you can prove uncertainty for much more general operators than just the Fourier transform. Just any operator that has these boundedness conditions. And in fact, it's more general than this. So you don't really need to deal with an operator and its inverse. Really, you can deal with two operators, A and B, both of which are bounded from 1 to infinity. And rather than requiring that B is an inverse of A, you can actually just require this weaker condition that the composition BA doesn't shrink the infinity norm. And in fact, you can even be a little bit more general. You can stick some constant out here, and then you recover the same constant in the primary uncertainty principle. And These operators are actually really plentiful. So we call operators with this property, with these three properties, k-Hadamard operators. And the reason is that they're related to Hadamard matrices in some sense, but they're really everywhere. So the Fourier transform is certainly an example of this, but there are examples also from coding theory, from block designs. There are relationships to quantum algebras, the fractional Fourier transforms. So they're really plentiful. And what this means is that using this technique, you can prove uncertainty principles for much larger classes of operators than just the Fourier transform. And I'll come back to this again at the end. But are there any questions about this before I go back to some more examples?
So at this point, you only use the boundedness of operators. In your calculation, you could have any other two norms, right? Instead of L1 and L infinity norm, you could just have.
That's right.
E to LQ also, right?
Yeah, that's right. So really, I mean, in a certain sense, 1 and infinity don't really mean anything in here. It's really, I have two vector spaces, and I have a pair of norms on this vector space and a pair of norms on this vector space. And I just need boundedness from the first norm here to the second norm here, and in the other direction again from the first to the second. Yeah, and I'll mention this again at the end, but actually it's sometimes useful to deal with other norms than just the L1 or L infinity norms. Yeah. Any other questions? Okay, great. So my third example concerns an uncertainty principle for other norm ratios. So here's the theorem. And as far as I know, no one ever observed this theorem before us, but it's another sort of natural uncertainty principle. So here, what we're saying is that if I pick any norm index P and I look at the L1 norm of F divided by the LP norm of F times the same thing for F hat, again, the product is lower bounded by 1. And again, this is an uncertainty principle in whatever vague sense this means, because again, if a function is very sharply localized, its L1 divided by LP norm will be small, whereas if it's spread out, this L1 divided by LP norm will be large. And something that's interesting is, right, the P equals infinity case of this theorem we just got by multiplying together these two basic inequalities, the boundedness of the Fourier transform. And so you might expect that also to prove this, you could, basically multiply together like the Hausdorff-Young inequality or something like that. But actually, I don't know of any way of proving this inequality that doesn't actually go through the L1 over L infinity result through the primary uncertainty principle. I'd be very interested if someone could find a way of proving this like directly. But here's the proof. Oh, and I might, from this point on, I'll keep showing the full proofs on every slide, but I might go through them in less detail just because it's not very interesting to watch me do calculus on the slide. But here's the proof. I mean, the LP norm of G is defined like this, or I guess the LP norm to the PF power. I can pull out P minus 1 factors of the L infinity norm from this integral, and I get exactly the infinity norm to the P minus 1 times the L1 norm. And I can multiply both sides by the L1 norm to the P minus 1. That turns out to be the right thing to do. And I can rearrange, and I get one of my blue inequalities. So what I find is that the L1 norm divided by the LP norm is at least some appropriate power of the L1 divided by L infinity norm. Right, so I mentioned at the beginning that sometimes it's useful for these blue inequalities to not just be that whatever you're looking for is some constant times L1 over L infinity. So here we're doing that whatever we're looking for is some power times L1 over L infinity. But anyway, once we get this blue inequality, we're good to go, right? Because we plug it in for F and F hat. We find that this product of ratios of norms that I'm interested in is lower bounded by some power of the thing I know how to handle and by the primary uncertainty principle. That's at least 1. So yeah, it's quite simple. Yeah, any questions about it? Okay. So the fourth example that I wanted to tell you about is to go back to the beginning and to do the Heisenberg uncertainty principle. And so I'm going to show you a proof of the Heisenberg uncertainty principle that's very different from the proof you'll see in textbooks, which again, the proof you see in textbooks basically uses this fact that the Fourier transform converts differentiation into multiplication by the variable x, and then uses like Cauchy-Schwarz. And the proof that I'm going to show you, again, is only coming from the primary uncertainty principle. So the only property it needs of the Fourier transform is just this L1 to L infinity boundedness. And because of this, you can also use the same approach to prove a variant of the Heisenberg uncertainty principle for many other operators. So again, here's the statement of the Heisenberg uncertainty principle. We're dealing with this variance functional, the integral of x squared against the norm of f squared. And that thing for f times that thing for f hat is lower bounded by a constant times the product of the L2 norms squared. And so just so we have room, I've put it up at the top of the slide. So again, we're dealing with this variance functional. And one thing that's interesting about this proof is that instead of using our usual primary uncertainty principle, the thing I'll actually be using is this inequality that we proved on the last slide, that the L1 divided by L2 norm of f times the L1 divided by L2 norm of f hat is lower bounded by 1. So previously we've used infinity rather than 2 in the denominator. It turns out that for this proof, it's more convenient to use 2. But of course, we derived this from the 1 to infinity version. So right, it all does go back to the same primary uncertainty principle. But OK, if I want to use this inequality to prove the Heisenberg uncertainty principle, what I need is, for any function g, a lower bound on the variance of g in terms of this ratio of norms, the 1 norm divided by the 2 norm. And once I get such an inequality, then I can plug it in to this inequality and prove the Heisenberg uncertainty principle. So the thing that does this is the following lemma. It's the blue inequality we need. And it says that the variance of g divided by the L2 norm squared of g is at most, is at least some constant times the 4th power of this ratio of norms. And right, once I prove this blue inequality, as I said, I can plug it into here, and then we get the desired result. So it just suffices to prove this lemma. And I won't do it in full detail, but it's quite easy. It's just 2 applications of Cauchy-Schwarz. So the trick is you pick some parameter t, which is defined like this. And then the thing you observe is that if I integrate g from minus t to t, I pick up at most 1/2 of the L1 norm of g. And this is just Cauchy-Schwarz plus how I defined t. And once I get that, right, at most half of the L1 norm of g is inside this interval. So that means that at least half of it must be outside this interval. I multiply and divide by x, and then I apply Cauchy-Schwarz. And what we see here is that I have the product of 2 integrals. The first one just converges. The first one is just square root of 2 over t. And the second one is exactly this variance operator that I'm looking for g, or rather the square root of it. And OK, I won't do the manipulations, but hopefully you believe me. You see that I have an inequality right now where on the right-hand side, I have this variance of g. And on the left-hand side, I have the L1 norm of g. And then I also have stuff involving this t parameter, which was the ratio of the L1 norm and L2 norms. So hopefully you believe me that after some rearranging, I can get the lemma that I claimed, which I mean, it is true. That is what you get. So by rearranging, you get this lemma. And then by plugging this lemma into this inequality, you get the Heisenberg uncertainty principle. So yeah, that's the proof. Are there any questions about this proof?
You get the same constant?
No, great question. You don't get the same constant. So the optimal constant for Heisenberg is known. It's 1 over 16 pi squared, if I remember correctly. We get a constant that's about a factor of 8 worse. We get like 2 to the minus 10th, I think. Yeah, and I think this is probably unavoidable. So somehow the optimal constant in Heisenberg is really a fact about the structure of Gaussians on the real line. And I would be pretty surprised if these very weak, very soft norm techniques could actually tell you something about the structure of Gaussians in the real line. So yeah, we get a weaker constant, but qualitatively it is the same result. Yeah, any other questions? Okay, so the things I wanted to mention about this. The advantage of this technique over the standard proof of the Heisenberg uncertainty principle is that it's very flexible. So using basically the exact same technique, except maybe Holder's inequality instead of the Cauchy-Schwarz inequality, you can prove the same sort of uncertainty principle for other moments of f, right? So if you remember in quantum mechanics, this norm of f was like a wave function, and so this norm of f squared was a probability distribution, and then this was actually the variance of that probability distribution. Now you could imagine that rather than caring about the variance, you might care about like the 4th moment or the 10th moment or whatever. And this technique can actually handle that. So, and another thing it can do is if you don't like the L2 norm on the right-hand side, you can get any other norm you want on the right-hand side. So if for whatever reason you wanted to prove an uncertainty principle of the form that, the 10th moment of position times the 30th moment of momentum is lower bounded by the product of the L14 norms of f and f hat, then this technique would give that to you. And yeah, so it's extremely flexible, unlike many of the standard proofs of Heisenberg. I should mention that some results of this type were proved by Cowling and Price. We can't prove everything that they do. They have some really general results that we can't get, but also we can get some results that they can't get, like allowing different norms on the right-hand side. And also our proofs are much simpler than theirs. I mean, it's all the same sort of calculus manipulation as what I was doing here. And yeah, I just mentioned this, the constant that we get is not optimal, and this is probably unavoidable. And for actually many of these generalizations, I don't even know how you would estimate the right constant. But certainly for Heisenberg itself, we don't get the right constant. Okay, yeah, any other questions about this example? Okay, so that was my last example. I'm going to start wrapping up. Before I wrap up, let me just summarize the things that we've seen. So the message that I want to get across today, and that I hope I've gotten across, is that many, but by no means all, uncertainty principles follow from this simple and general framework, where you start with this primary uncertainty principle, that the product of these norm ratios is at least 1. And after you prove the primary uncertainty principle, if you want to prove any other uncertainty principle, you just prove these universal bounds relating this quantity to whatever measure of localization you want. And that all works on the level of a single function rather than on a pair of a function and its Fourier transform. The other thing that I wanted to sort of reiterate is that the standard proofs of most of these uncertainty principles use either heavy machinery or special properties of the Fourier transform, or both. And we don't need either. We only use these basic boundedness properties of the Fourier transform and just calculus, basically. There are obvious shortcomings. So, I mean, right, I mentioned already that you don't always get the right constant. And also, you certainly can't prove, or we don't know how to prove very many uncertainty principles that can be proved with other techniques. But I think that these shortcomings also lead to interesting questions. And the reason is that if, these results are very soft, or these techniques are very soft, and if you can't get the right constant, or you can't prove some result using these techniques, that suggests that that result, or that tight constant, is actually telling you something deeper than just what these soft techniques are picking up on. And so this is hinting at some, deeper truth that's hiding there. And the final thing that I want to reiterate, which I'll go into more detail about in a sec, is that the only property we needed of the Fourier transform is that it's bounded from L1 to L infinity, and that its inverse is also bounded from L1 to L infinity. And because of this, all of these techniques work in much, much greater generality. So I just want to give you some examples of this. So again, this is what I had written on the previous slide. So what is this greater generality? So we can just use these techniques to prove uncertainty for many more operators. So in the continuous case, a nice natural class of operators that satisfy these boundedness properties are what are sometimes called linear canonical transforms. So I've written here the definition. So given a matrix in SL2, you define this integral operator. Turns out this is the right definition, but you see that it is integration of f against some function of some complex phase, something of norm 1. And because of that, this will also have this L1 to L infinity boundedness by the same reason. And so you can prove uncertainty for these linear canonical transforms. I think this thing is, so for some reason, people in optics really care about these linear canonical transforms. I think this is also sometimes called the metaplectic representation of SL2 acting on L2. But anyway, it shows up in a bunch of places. It also generalizes things like the fractional Fourier transform and the Fresnel transform. So this is just a wide class of operators for which these techniques work, and you can prove uncertainty principles. And in the discrete case, we can also get a large number of operators for which we can prove things. So first of all, many sort of structured matrices, linear operators, have uncertainty principles. So these include Hadamard matrices, various types of matrices that are studied in like design theory, so conference matrices and things related to discrete geometry, matrices coming from error correcting codes. All of these you can prove uncertainty principles for using these techniques. And another nice thing that I want to mention is you can check that if you pick, say, a unitary matrix or an orthogonal matrix at random, then with high probability, it will also have these nice L1 to L infinity boundedness properties, both it and its inverse. And what that means is that almost every matrix, in this sense, satisfies an uncertainty principle. And so somehow the Fourier transform maybe isn't so special. Almost every matrix has uncertainty built into it once you look at it from this perspective. And so to wrap up, I just want to leave you with a couple of open problems and more things you can do. So again, here's the most general theorem that we can prove of this type, where you have these two operators A and B, and you assume these boundedness conditions, and you derive this primary uncertainty principle. And yeah, as I mentioned before, really 1 and infinity here aren't really meaningful terms. This really works for arbitrary pairs of norms on 2 vector spaces. And this is actually very useful. So if you want to prove uncertainty principles for non-abelian groups, then it turns out to be very useful to not deal with the standard L1 and L infinity norms. It's useful to either deal with some appropriately weighted L1 and L infinity norms, or to deal with the Schotten1 and Schotten infinity norms on some space of matrices. Another extension you could do of this is, rather than just having 2 operators, A and B, you can have any number of operators. So you can have A1 up through AN, and you assume that they're each bounded from 1 to infinity, and you assume that the composition of all of them has this property, that it doesn't shrink the infinity norm. And then you would get an uncertainty principle relating, F, A1F, A1, A2F, and so on. And for a while, we thought this would be useful. We had an application in mind, but then it didn't end up working. And I'd be very interested to hear if someone can find an application where you care about uncertainty for, the value of F under multiple different operators. Another thing that I want to mention is that linearity of these operators isn't really relevant. So you could try to write down a version of this where you allow A and B to be nonlinear, assuming you appropriately define what it should mean for some norm boundedness. But I don't know of any examples of nonlinear operators that satisfy the appropriate conditions. And I'd be very interested if someone could find some nonlinear operator that has uncertainty. And the final open question that I want to mention, which was something we worked on a fair amount and weren't able to do, there's a multidimensional version of the Heisenberg uncertainty principle, and it's basically what you would expect it to be. So now F is a function defined on Rn, and the variance now is you integrate the L2 norm squared of X against the norm of F squared, and times the same thing for the Fourier transform, and you get some lower bound. And the important thing here is that the lower bound is quadratic in n. And we don't know how to prove this result with the correct quadratic dependence on n using our techniques. And I don't know if this is just that we haven't found the right calculus tricks to relate this multidimensional variance functional to the L1 divided by L infinity norms, or if there's really a fundamental obstruction. And I'd be very interested to know whether you can actually do this using our techniques. And yeah, that's everything I had prepared. So thank you for your attention. I'm happy to take any questions.
Thank you so much for a beautiful and pleasant talk. We can open for questions and comments now.
Beautiful talk.
Thank you.
Yeah. Yeah, one often forgets when one does that with all the epsilon delta struggling that it's actually a beautiful subject for analysis. If one, yeah,
Yeah, I agree.
yeah, and you really showed it. Yeah. I will recommend your talk to my students because I'm doing a reading course on Fourier analysis where we struggle through all the theorems, and I will tell them to watch you.
Oh, thank you.
Well, there's a question in Q&A. I will let you read.
Okay, one sec.
You need to click on Q&A.
Yeah, yeah, got it. Yeah, so, right, this is, I think, yeah, so the question is, you know, that the primary uncertainty principle implies the uncertainty principle for some measure of localization. And so, yeah, there's no, I don't have, right, so the thing that I would love to be true and that I don't know how to make true is, you know, it would be great if you could write down a set, I don't know, L, which would be, you know, all measures of localization. So, right, it would be great if you could sort of define what it means for some functional to be a measure of localization. And you could get the set of all of these, and then you would prove that actually, you know, for all L and L, you have that, I don't know, L of G is at least, let's say, some constant times the L1 norm of G divided by the L infinity norm of G, maybe to some other constant C prime or something, right? So if you could actually prove a theorem of this type, then you could really say that any uncertainty principle which concerns measures of localization that satisfy whatever axiom you have actually can be derived from this primary uncertainty principle. But I don't know how to do this. I don't know if it's possible to do this. So instead, all I'm claiming is just that for many things that you could naturally call measures of localization, such as the support size or this variance functional in the Heisenberg uncertainty principle, for certain of these special ones, you actually can do this whole operation. But I don't know of a way of doing it generally. I don't have a technique for, yeah, I don't have some general purpose way of doing this. It's just for some specific measures of localization, we can actually do this. Yeah, so I don't claim a theorem of the form, any uncertainty principle can be derived from our technique. The only claim is these certain uncertainty principles, like the ones I showed you, can be derived. Does that make sense? Does that answer the question?
Let me give him.
Yes, thank
Yeah,
you
go
very
ahead.
much.
Great, thank you.
So just a question about the high dimensional thing that you asked. So is the quantitative problem genuinely continuous, or is it also in the discrete one? So if you try to recover, you know, this optimal uncertainty principle on the Hamming cube, for instance, can you, there was something by Polyansky and some years ago.
That's actually a good question. Right, so I would expect that it probably is equivalent to some discrete thing on the Hamming cube. Yeah, there are all these results that show that various like hypercontractive or log Sobolev or things like this in Gaussian space sort of correspond to limits of something on the Hamming cube. So it's possible that you could derive this from some discrete thing, but I don't know exactly what the discrete thing would be. And I also don't think that I know how to prove that discrete thing using our technique. So for instance, just the one-dimensional version of Heisenberg, the proof I showed you is the only proof I know using our technique. So I don't know how to derive it from some appropriately discretized thing. But it's a good question, and I have to think about it more.
Okay, but already there is, I mean, in the discrete one, without caring about the continuums, there is a bound which is somehow, which has a correct asymptotics on the dimension. So maybe this could follow as well from the technique. I don't know.
Yeah, that's, yeah. Yeah, I think that's a good point. I'll have to think about it some more, but I think what you're saying makes sense.
Okay, thanks. Very nice talk.
Thank you.
Thank you. Are there any
Ask
other?
a question.
Go ahead.
Among the examples you mentioned was the result conjectured by Hirschman and proved by Beckner, where you had a sum rather than a product of functionals. You simply take logarithms or something, and this works out. Can your method work there?
Yeah, that's a great question. So yeah, there you had this. It was h of f plus h of f hat is at least whatever it was. I think it's log of e over 2. Right. So you could certainly imagine that you would prove something, I guess, of the form like e to the h of f times e to the h of f hat is at least something, and then you could hope to do this using our technique. I don't know how to do that. I think it's probably possible, but I tried and wasn't able to make it work. And again, I don't know, it's really hard to tell with all these things if there's some deep obstruction or if just there's a bunch of different calculus tricks you can try, and I just didn't try the right ones. The one thing that I will say is I am basically certain that you can't get this correct constant using our techniques. And the reason is that Hirschman proved a weaker lower bound with just 0 here, which is actually pretty easy. It just follows from Hausdorff-Young. And that might be possible with our techniques. But to get actually the correct constant here is basically equivalent to Beckner's sharp Hausdorff-Young inequality, which is a really deep and difficult statement. And so I would be shocked if you could prove something like that using these very soft techniques. But I do believe you should be able to get something. And I was rather frustrated that I was never able to get something. And yeah, I'd be very happy if someone could figure out how to make this work. It certainly seems within reach. I just don't know how to do it.
Just informally add greetings from the Technion.
Thank you.
Great pride and pleasure that one of their students and his family have got such wonderful things.
Yeah, thank you.
Are there other questions, comments? All right. If not, thank you so much, Yuval, again, for a beautiful talk. We appreciate that. So,
Thank you.